All right, so this talk is about Ohm Next. I have a lot of slides, so we're just going to get started. It's going to move really fast. I'm not going to give too much context. I'm sorry that I may say some things you've not heard before, but I have a bunch of other talks that are much slower paced that I recommend watching if some things are confusing, and then come back to this one. OK, so most UI distributed applications that have a significant non-trivial UI component in the mainstream, they look something like this. You have some mutable code on the server, generally written using some REST framework. You're communicating JSON, so it's some ad hoc message exchange format. You've encoded some date on the wire. You're praying that the client will parse that correctly. The client is generally written in some mutable language, often JavaScript, with some mutable framework. And so it's not surprising that you run out of your complexity budget really, really, really fast. And if you've done this enough times, as I have with traditional systems, you may be a little bit excited about doing it a different way. So you may say, well, let's do something conservative. Let's switch out this the message format with something that has stronger semantics, just the foundations, like dates. We don't have to talk about dates anymore. We can move dates across the wire, and that'll be great. It doesn't really fix the system, and then so you may attend ClojureConj, and you're really excited about simplicity and simpler systems, and you decide you're going to use Clojure on the back end. And then the back end team is really, really, really excited because it's easier to test, it's easier to reason about. Maybe you take it a step further and use Datomic, and then party time on the back end. And the front end people, they start getting jealous. They're like, oh, the back end, they're having so much fun. We want to have fun too. We also want to reason, have more reasoning capability about the front end, and you may decide to use ClojureScript to achieve this, and maybe React. Now, sorry, I'm going to turn this off. So this is awesome, right? You magically have a great system. Sadly, that's not the case. You won't magically have a nice system. And why won't you? And the problem is, in the previous diagram, while you may have increased your ability to reason about the server-side component, and you may have increased your ability to reason about the client-side component, nothing in that diagram, with the exception of transit, really gave you any more confidence in the relationship between these two parts. Richicki has a bunch of great talks. I think this is one of his more underappreciated ones. And this talk is very much a riff on the language of the system, but with a sort of UI-centric focus. So what are the problem statements? It's always good to start off with problem statements. These are what I see as problem statements. So it's definitely, I'm a bit biased with my background in UI programming. But I see them as, there's a lot of ad hoc stuff. You look at a code base and there's a lot of ad hoc stuff just about how do the client and the server even speak to each other? Do you have random components making requests? And then usually when this happens, that means usually those components are caching state, and this really contributes to the problem, that it's all the communication itself is ad hoc. There is a deeper problem beyond this, which is the client-server relationship often requires too much out-of-band information. For example, how can you know when you make a request to AWS, how do you know what you're going to get? Right? You don't. You have to read the docs. That's the only way to know. All the information about the relationship is out of band, and so we want to fix this, and that's a big idea in Ohm Next. There's a side thing, which I don't have enough time to talk about, which is that React is great, but we're not cargo culting React. React actually creates a lot of problems, and people don't want to talk about this, and I talk about it all the time. The React rendering model is a waterfall model. It's great for doing functional stuff, but you have this issue where if you want to go back up the component tree, or you want to move sideways, React makes this really annoying. And this is the reason why things like Flux and Redux exist. They're all trying to fix this problem with this waterfall design. And Ohm I try to actually really solve this problem at the same time as I solve some other things. There's some assumptions. Ohm is very opinionated. There's some basic things. I'm not going to explain them. It's just what I believe. Single atom app state is just awesome. This is just a great idea. It makes it easier to test your application and reason about your application. Overflushing is bad. Ohm uses a asynchronous rendering loop. We try to render at 60 frames per second. We don't want people to be in charge of flushing. So this is a new thing. This is quite different from the previous version of Ohm. And now I believe that visible asynchrony is bad. So in early Ohm tutorials, we often would use core async for something. I just think it's a bad idea. The Ohm Next model is completely synchronous. You need asynchrony, but it should be outside the components themselves. Components look pure and they look synchronous. Asynchrony is completely at the edges of the system. A visible event model is bad. So having used many UI frameworks in my career, I've just come to the conclusion that event models are terrible, and they don't fix any real problems. What usually happens is that people wire things together. There's one little event, somebody clicks a thing, you have a massive event cascade, and you really are looking for how did this happen? Who changed what? And so OMNext completely throws out any visible event model. And so we'll see how we can still recover synchronization of the UI without that. OK, so what's the goal? The goal is actually really simple. I have two things that I want to accomplish with OMNext. One is that clients should be able to make precise, non-trivial reads simply. This is not something that's easy to do in most systems. You want to be able to actually say, this is exactly what I want, because I want to render it immediately. I don't want to transform it. And this should be easy to do. There shouldn't be a lot of ceremony around this. The other thing is that this is something that actually, some of the systems that support the first thing, like Relay and Falcor, they don't support the second thing. That communicates, clients can communicate non-trivial novelty in a simple way. So it turns out the goal is actually a labyrinth, right? So even though the previous two things sound simple, they sound desirable, they create a host of problems if you want to achieve those things. And so when you look at OMNext, you might be, why was it done this way? And this talk is actually showing you, if you want to get the first two things, you have to solve all these other problems in order to get there. So let's talk about some of the obstacles. I mean, some of these should be obvious. If we're going to do this, what does it mean for clients to make precise requests? What does it mean for servers to handle precise requests? What does it mean for clients to communicate non-trivial novelty? What is it going to look like? How do servers communicate identities? So this is an interesting problem, right? So often clients want to support the user constructing some non-trivial piece of data, but the client doesn't have identities for those things yet. So when you send it to the server, how are you going to keep those identities in sync? Most people just give up, and this actually itself introduces a lot of complexity, because the client has some piece of state that it needs to update once the server knows the truth. Integrating novelty in client, once the novelty comes back, how do we update the UI, stuff like that. Another interesting problem is local state, right? So there's state that the client wants to represent, which has no reification in the database. Like, what's the currently edited thing? You probably don't need to put that in the database. This is something that's only present on the client. And does the problem of local state complicate these other decisions we may make for these previous things? Once you think about client local state, then you have this problem like, well, if you solved it, are optimistic updates simple? An optimistic update is update the client. We know it's probably going to succeed and just send it over the wire, and everything will be OK. And this is good UX design. What about testing? If we do all this stuff, are we going to make testing harder, or are we going to make it easier? What about standard UI patterns? You often have recursive UI components. Do any of the decisions we make this easier or harder? What about caching? Do any of the decisions that we make caching easier or harder? So Falcor and Relay, for example, currently have no good story for using traditional HTTP layer caching or client-side caching. And then how flexible is the system? You may be building an OMNext thing and decide, actually, I want to have the same schema in Datomic and DataScript, and I want to pull something from Datomic and just transact it immediately into DataScript. You might not start your project that way, but maybe that's what you want to do. How easy or hard is that to do? Custom server. You may decide to be more conservative in the back and you want to use Postgres. You start with Postgres, then you realize it's just way easier with Datomic, way better with Datomic. How hard is the transition to Datomic? And then other concerns like, I'll talk a lot about a request response cycle, but there are a lot of applications these days that want to have live streams. So is it easy to subscribe to some live stream of events being from the server and integrate that into the request response cycle without creating a lot of complexity? I'm going to answer all these questions. I have 93 slides. I hope you had drink a lot of coffee. We're going to go really, really, really fast. So what do precise requests look like? OM solves this with query expressions. What are query expressions? They're simply a riff on Datomic pull. They're not exactly Datomic pull, because we need to be able to do more things. The way that pull works, you have to use it in combination with query. And we actually want the pull syntax to be good enough for basically generic querying, and as well as mutations. And we'll see this. But the point is that you can bottom out in Datomic pull pretty fast. So you can have these queries, and they bottom out in Datomic pull, and it'll just work, or DataScript as well. OK, so the idea here is we co-locate query fragments on UI components via static methods. We stole this idea from Relay. Right? This is exactly the way that Relay and GraphQL work. And what this means is that you can take the root view of your UI. There must be a root view, the bottom of your UI. And we can ask that the thing the class is going to render without even instantiating it. We can ask the question, what is the total demand for everything in the UI that we're going to need to display once we get the data back from the server? This is awesome. This really answers the how. Right? Components are no longer involved in getting the data themselves. We now have a very powerful model for always being able to get exactly what the application needs, and we only need to make one request, which is huge if you're talking about mobile clients. So it looks something like this. I've sort of hidden the parts that don't matter. You make a little static method, and you have this datomic-like pull syntax on your query. Because it's just data, it's just Eden data, we can recursively compose this. Right? We can just ask the other types that are involved in the UI what their subquery is, and we can just build this whole data structure. Simple reads looks like datomic pull. Here, if you say you want to read the address of a street, just a keyword, you want to get somebody's first name. There's another thing that we support which looks a lot like datomic lookup refs. We call these idents because they serve another purpose in OM, which is it allows two parts of the UI that represent the same logical identity to be automatically kept in sync. And we'll see this later. We support parameterized reads. If you have a query syntax, you need to be able to take a key, some key, and you want to parameterize it. This is exactly the same as URL parameterization. This is a two-element list. What's the key you want, and what sort of other things do you want? Are you interested in? There's no restrictions on this what can appear in the parameter part. It's just like URL parameters. It's up to you what those mean. Joins. So this is big. So this is definitely treading into Relay and Falcor territory. The problem with REST-based systems where you really have this clean, resourceful thing is that, well, how do clients get related resources? It was fine back when people had fast internet to just go back for more stuff. But as on devices that are more bandwidth constrained, this is not really that great. And actually what happens is that people, in order to solve this problem, they just arbitrarily put some random collection of related resources behind some resource. And it's never the right set, right? The client will probably want something else. So even when you do this, clients still need to make multiple round trips. So we're going to get out of that. So here, this is what a join looks like. So I might want to get a to-do items, and then I can recursively subselect the properties that I want from that, right? So this is just turtles all the way down. All right, so once you have a query expression, you need to be able to evaluate it. And so we call this parsing. It's very similar to routing, but I called it parsing because it just seems more natural. You go from some query expression to some other value. Parsing is just evaluating a query expression. We take query expressions to some Eden value, but it's important to understand this Eden value is the UI data tree that you're going to render. You're not going to do any more transformations on this thing. So the query expression gives you the thing that you can supply to the UI component, and you're done. There's nothing else to do. Now, what does this look like? Here's the most simple parser. So we make a read function. There are two types of parsing functions. One is read and one is mutate. So read is very clean. It's side effect free. It takes 3 arguments. It takes an environment. It takes some key that you're currently parsing. And it takes any parameters if they were supplied. You can make a parser just by saying, here's the parser. Here's my read function. And here at the bottom, I say, on an empty environment, because I'm not supplying anything yet, given this query expression, give me the UI data tree back. And in this case, it's just trivially foobar, right? So the function simply says, these are the values that we supply for particular keys. Then you have, I changed this slide just a tiny bit. And what happened here? Right? So instead of returning a value, I returned remote true. And parse no longer returns anything, because it can't. It doesn't know it doesn't know what that is. It doesn't know what that thing is. Right? It doesn't live on the client yet. So we can change that, and we can add, well, we want the query expression that we can send to the remote thing. And so this takes query expressions to query expressions, right? So this is the message that you can send. And all this stuff is automated, right? It's automated. OMNext will automatically run the query, get the UI data tree, render what it can, compute the thing that it can't figure out, and send it over to your endpoint that you've specified. OK, so what does handling precise requests look on the server? Looks a bit like this. Notice it's surprisingly similar to the client part, right? So this is just the Falcor idea. In Falcor, you have these routers that live on both client and server. And so we just, again, stole a good idea. So here we have a read function which returns something for to-dos list, the to-do list key. Notice that the environment now takes something meaningful. It's the connection, in this case, datomic, and then whatever the pull syntax query is going to be that we pass along. Right? So now you have a way, you have a unified language on both client and server. Right? So we're starting to see that we're eliminating this problem where the relationship between the server and client is meaningless. Now it's meaningful. And then you can construct a parser, and you can pass along the connection, and so on and so forth. Right? So this is because the parsing code is in a .clgc file, so it works both in Clojure and ClojureScript. OK, that sort of demonstrated the request, sort of the read cycle. So now let's talk about communicating novelty, because clients need to change the system. So it looks something like this. So this is a transaction query. It's just a query expression. But the difference is that the very first element here is a 2-element list. There's a symbol, and the symbols, this has to be this way. The symbols name mutations. And you can pass along parameters like you could pass along parameters with keywords. This is the thing that's going to change the system, right? And this is often non-idempotent, right? This may change many things of your system, right? There's this interesting thing here, and this is why we can destroy the need for a visible event model. And this is, again, we're just stealing ideas from Relay and Falcor. So you run a transaction, and you wrote the client, and you know what keys you care about. You know what keys are going to change, right? So there's no event cascade. What's going to happen is this is going to submit something to the server, and then you're going to say, I know this is going to change. Let me reread these keys, and we just update. So there's never an event cascade to look for, right? You always run a mutation, and you specify the keys you want to read. You might be wondering, well, how do you know what you want to read? And we'll demonstrate that in a second. So here's the simplest mutation function. Notice that the signature is exactly the same as read. You have an environment map. You've got the key that you're mutating, whatever that thing mutation is named, and then whatever parameters. You can't run this mutation locally. We just return remote true. The parser runs in remote mode, and it returns this thing that we're going to forward to the server. So let's handle that mutation request. So here we have a mutation. It doesn't look, it's really good. It's almost identical to the way that reads look, except you return a map that has a value, which I'll explain in a second, but it has an action, the action that will actually apply the mutation. And this has to be in a thunk inside of a function because we really want parse to be side effect free. We often need to run it in multiple times. We may need to compute multiple remotes, and of course we need to run it to compute what we're going to render. So down here, on the server side, we run the mutation, and what it's going to return is we ran this mutation, and here are the set of keys you might want to reread, right? We don't want to force the client to reread this, right? So Facebook and Netflix already figured this out. Netflix needs to work on set-top boxes, mobile phones, watches, desktop computers, right? There's all types of display information that may change. Different clients will want to read different keys, right? So they already thought through this problem. That's the path they took. It's a good idea. We're just going to follow it. We communicate what might have changed, but it's the server who observes, OK, if I do this, this changes. This is what I care about. And this is what I want to reread. There's another thing that's interesting here is we have the lookup ref pattern. This pervades OmNext. It's super useful. This is how the server communicates identity. This is how identity is represented on the client, 2-element vectors. Which brings us to the Temp ID problem. So OmNext just copies Datomic, because Datomic has this really great thing where you can build up a transaction, right? You can build up the entire transaction. You can use Temp IDs to say, these are the links between the data. And then you transact it, and then Datomic tells you, this is how you go from the Temp IDs you had to the real IDs. But this is awesome, right? This is awesome. You have a model now for clients to create non-trivial novelty, committed to the server. The server can say, this is the Temp ID transition, and Om can automate the entire thing for you. You don't have to delete temporary data, right? User builds up data, server communicates identity, done, right? It's just not your problem anymore. Again, removes an incredible amount of complexity. If you've ever done anything non-trivial, this problem is terrible. So what does it look like on the client? What will happen? So here's some state. We'll explain the actual layout in a second, but notice there's like this temporary Om ID thing, right? Who cares how it's represented? It's just something that the server can understand. We'll We'll write something on the server that creates some novelty. And then we'll say, well, we got the old ID, and here's the new ID, the one that we know about, the one that's the real one. And it just passes us back along. Next sees that your mutation returned a temp ID transition. Boom, done. There's nothing to do. There's no code you have to write, right? There's just a way to move identity back to the client. This is awesome because I live in New York, and network connectivity is very spotty, right? With this model that I just showed means that you can basically build non-trivial amounts of novelty. You never have to talk to the server until you absolutely have to. And this is great when you have slow networks, and it's great when you don't have any networks at all. What about client-only state? So here's a huge problem, which is that you have state which you'll never put in the database. It'll never be there. It won't exist there. It'll only be in the client. Again, things like temporary transitional actions and stuff. So Relay doesn't support this at all. And in fact, I chatted and like, well, what do you all do about this? And users have to hack around it because they want it, but they can't represent it. Falcor actually does support this. It's great. They do this by nesting data sources. And OhmNext supports this very well. It means that you can actually have graphs that will never get sent over the wire. You may have some keys, and they never exist on the server, and you can parse them, and the remote parser doesn't need to know anything about it. Right? This allows us to preserve a separation, but then also share the things that need to be shared. So it's a unified data access model. We just steal the Falcor version. Right? We just do what Falcor does. It supports this merged view of client-only state, server state. So what does the client state look like? Right? We haven't talked about that. We saw that a little bit in the previous slide. But what has to happen is you have to take trees, because the server responds trees. Right? This is true for both Relay and Falcor. But you need graphs. Right? You need graphs. You need to update graphs. This is actually one of the biggest flaws in Ohm, the original Ohm, is that you have to work with trees. And this was very obnoxious, and it created lots of problems. It's also the problem with React. You have to work with trees. You want to work on graphs, because graphs are easier to update. So here's some data that the server responded with, or maybe you created it. And the problem with this data, it's very typical, is that this is great to render. It's very nice for rendering, but you have duplication. So updating this is complicated. You have to remember all the places you want to update this thing. And you don't want to do this. There was actually earlier versions of OhmNext where I tried to make this work, and I gave up, and I realized that Relay and Falcor were just correct. You want normalization. So Falcor, it's a bit annoying. And so there's a lot of, I didn't want to do the boilerplate that Falcor requires. Falcor, you have to build the normalized representation manually. It's not fun. Relay just does it automatically for you. And it's able to do this because it has queries. The queries give you enough information to do it. You do need one other thing, which is, when I'm at a node, what's the identity for this node? So you can replace the value with a link. And you supply this. And again, this actually has a dual purpose. You can have the same logical entity rendered by two different things. And because they have the same identity, OhmNext can keep them in sync. So it has a dual purpose. It allows us to normalize the tree, but also allows us to keep things in sync. And it's automatic. You don't have to do anything. So what does it look like? We just replace that first thing with a link, a two-element vector. It looks like a lookup ref, and we moved it into a table. Notice that the vector is something we can use with getin. Right? Getin just works. That's another point, the other point in using the two-element vector. Now we get to Mary, and we want to replace both instances, right? There's links now for both those cases, and we move it into a table. We merge the keys, because different components are going to want to read different keys, right? We create a merge thing, a merge map. And now if you want to update Mary, you only need to do it in one place. And the UI will always stay in sync. Right? It doesn't matter how many times the same identities appear in your UI. It's very simple. It means there's no complexity around identities and keeping them in sync. And once you have this format, what stops you from putting your own keys there? Nothing. Right? You get a response from the server, and you have some keys that you don't want to put in the DB. And this is trivial. Just add a key. You know what the representations of the links are. Add a link. Right? You now have a way to create a merged view of the state that's here, the states that's there. OK, so now that we know that we can do this, what do optimistic commits look like? Right? We want to run some transaction, and then we also want to send it over the wire. This is all the code for an optimistic commit. That's it. It's just this one thing. Right? We have the transaction at the bottom, this action, which transitions the local state, And then we just say remote true. And Ohm will automatically pass that on, get the data, and if it's the same, nothing happens. And that's pretty cool. Okay, testing. What are the implications? So there's a lot of new stuff that you probably haven't seen before. And what does this mean for testing? It actually has huge implications for testing. So having worked on UIs for a very long time, the testing story for UIs is generally a bit of a joke, right? In order to get sophisticated testing, you have to use really sophisticated, complicated frameworks. Most people just give up, and they just have QA teams sort of labor on all these different types of devices. Often you say, well, we can't test all the devices, so we'll only really test the three that people actually have, right? The testing story for UIs is, pretty comical. But how can we gain confidence? We know why it's hard, but how does what I just showed make it any easier? How can we know with confidence that our UI state transitions are going to be the same everywhere? Well, what did I just say? Parsing gives you the UI data tree, right? So functional programming is going to rescue us. Next parsing creates the UI data tree. Your components are pure functions from the UI data tree to the rendered DOM, right? There's a direct correspondence, completely direct, right? You don't need to look at anything. You can prove properties of your UI without ever looking at anything at all. And so we're going to use TestCheck to show a cool demo. They're actually much cooler demos than the one I'm going to show, but you'll get the basic idea. The other thing is because the query expressions are themselves data, they're data, you can generate them. You can generate transactions. You can basically generate transaction streams, right? And so it doesn't matter, I may use a gesture that triggers a transaction. I may use a mouse that triggers a transaction. I may use a Braille keyboard, it triggers a transaction. Who cares? Who cares how we create it? We can model all users just by generating transaction streams. It's important that TestCheck is actually monadic because if you're going to generate these streams and you want to model the user, you need to be able to thread state. And so TestCheck has a good answer to this problem because they really thought it through. So you can verify now that the UI data tree will have the properties after the transactions are applied, and we'll demonstrate this. Again, there are much cooler demos that I have, but I don't have that much time. You can ask me about this later. So here is some data. It's a friending application, and I want to prove some properties. I want to prove that but gain confidence that if I add a friend or remove a friend, is the UI data tree consistent? Is it still consistent? So here we have some people, and they have friends. And of course, friends are also people, right? So here I'm going to render a friend, and we have this identity function, which takes this, will take things that appear here, and it gives us an identity for that thing. And the query says, I want to read ID and name. Person. Notice that the identity function for person is the same as friend because we're going to want to keep these in sync. If somebody changes their name, you want to change their name everywhere. And then this person has a query, and friends is computed from a different component. So this is the recursive composition of queries. And then we have the root of the application, in this case, a trivial application, which is people, and we're going to do this. And so if I can go get query, people, boom. That's the total query for the application. And then we keep scrolling down, and we see reads. They look exactly like what we've already seen. We have mutations. Here's an adding friend mutation. We update the atom, so on and so forth. It's pretty straightforward. And then down here, we have the parser. We've already seen that the parser is always constructed from a read and a mutate function. And here we have a generator which creates random transactions. We're modeling the user. And so we can go sample 10, right? These are the transactions. We can just use these on the UI state, and we're done, right? We can just run this stuff. So I want to be able to prove in my UI that it's impossible for a person to appear in their own friend list. This should be impossible. There should be no path, no user-generated path for this to happen. And look at this. So we're not looking at anything. We can just prove it, right? Or really be very confident, not prove. I keep saying prove, not prove. John Hughes would be very annoyed that I said that. So here we make a parser. We supply a read and mutate. Here we say take the initial data, normalize it, create the state atom. We take the randomly generated transaction. We apply it to the state. We use the parser again to get the UI data tree that's the conclusion of running that transaction. And then we run this check. Is there any place in this tree where a person appears in their own friend list? And so I'm going to demo this. So we're going to, So we're going to do quick check, and we're going to go 100, and we're going to go prop, no self-friending. I'm going to run this again. And what's cool, right? So the awesome thing about property-based testing is that here's some random thing that it generated, and then it shrinks it to the minimal user interaction that caused the failure, right? Yes, a person can add themselves as a friend. So I go up here to add friend, and I review the code, and I see, oops, I forgot to say only if ID isn't equal to friend. And I return this, and I save, and I wait for Figwheel to update. Boom, right? You have an entire model for modeling users, right? You can model streams of user interactions, and you never have to look at anything, and test check can give you the minimal sequence of user interactions, right? And the reason this can work is because OhmNext says the way you should model your application is that parse returns the thing that you will render, and you should not change that thing, and that gives you really powerful testing capabilities. Okay, so I would rather, and the idea here is, right, what this will let you do is that now when you're QAing important stuff, like are the animations smooth, right? All right, does the style look good, right? You're actually doing quality assurance. You're not having them, these basic bugs, right? You want to eliminate this massive class of bugs, and again, you want to eliminate them universally. You want to know that it is not going to be the case. It doesn't matter where your application runs. Okay, so we have this query syntax, and does this make some things annoying? Like if you've done a lot of UI programming, inevitably you have to use recursion somewhere. So is it bad to use these queries, and does that make it harder to write things like outliners, things that are naturally recursive, and directory views, and so on and so forth? No, because Datomic already solved this for you, right? Datomic has this recursive little thing, and this just works. And people are already building systems using this, right? They can naturally write recursion into their queries, and here is this UI element will actually invoke itself, right? Again and again, and it just works. It's important that it just works. If this didn't work, I probably would have not done OhmNext at all. This had to work. Okay, what about caching, right? So this is the big thing because when I worked at the New York Times, I enjoyed my time there, and I enjoyed working in Rails. Rails was very productive. But Rails is not that fast. People know that. This is not a problem. But it's OK, because you can solve that problem with the caching layer and being smart about caching. We used Varnish. And I really saw the value of this. It may be the case that you're building a system, and you really can't make the query faster, and you need to implement some form of caching. So caching is good. Relay and Falcor throw out traditional caching techniques. They just throw them out. You cannot apply them in their current state. And when I saw this, I was like, well, I could go there, but I really suspect that nobody will want to use these systems until they solve this problem. And I said, I think we can solve this because our query expression is data, and that gives us a lot of power. So we don't want to do what Relay and Falcor do because they introduce a lot of novelty. They're already talking about things that I don't want to hear. Things like, oh, there's going to be a client-side TTL and all this other stuff. You're like, or timeouts and cache eviction policies, and you can apply a strategy. Don't want to do any of this, right? The browser already solved this problem. There's all this stuff inside the browser and things you can do at the HTTP layer that solve this problem for you. We don't want to go there. So OhmNext, out of the box, supports traditional HTTP caching, and you can just reuse the existing technology. This is very much like, this is the system that we live in. Let's reuse the parts that work. So we solve this with the notion of multiple remotes. So you've only seen one remote, and we can solve this by supporting the idea of multiple remotes. And basically, you can take your total query, and you can identify where things should go. This part of the query tree goes here. This part of the query tree goes there. And because it's Eden, and because ClojureScript implements Clojure persistent data structures, and in fact, they hash the same way. We use the same Murmur3 hashing algorithm. You can know that this per-stir on this Eden data structure will always hash the same. You can SHA-256 the thing. You're going to get a stable URL. So imagine I'm making a live dashboard. It's going to include posts, photos, graphics. This part of the query, this portion of the query, is dynamic, just the user's favorites. Whether the currently logged in user has favorited some item in the stream. that has to go to the dynamic endpoint, right? It just has to be served for every single user. But the large part of the application isn't dynamic. Every user is going to see the same thing, the same stream. So we can just elide that part per stir, and then just do the SHA-256. And you're going to get the same URL on every single client. And then it's back to the traditional caching you've known and loved for many years. So we just fixed that problem. OK, so customization. So you might want to customize client storage. And so OhmNext supports this out of the box. A lot of people like DataScript, so we make it work. DataScript is fully supported. People are already building things where they have the same queries, they have the same schemas, and again, they can just hit an endpoint, get back this, the entity map tree, and they can just transact it immediately into DataScript, and it just works. Pretty cool. Sorry, I skipped that last point, but I said it. Server side, what about server side? The OhmNext model is actually back-end agnostic. It's completely back-end agnostic. You don't have to use Clojure if you don't want to. I think it's a terrible idea, but you can do this. It's going to be easier if your backend language supports transit. So that's kind of like the minimum requirement. What's nice is that supporting HTTP caching relieves pressure for server-side novelty. So you may have an existing system. You will use it with Clojure. You really like the ideas behind OhmNext. And HTTP caching will allow you to transition over time to a database that's better suited for this model of programming. Right? So when you get there, you'll be able to swap into Atomic, and it won't really be a problem. OK, streaming, last sort of customization thing. OhmNext just out of the box, the way I designed it, it just supports side loading. Right? So you may have a request response cycle, but then you decide, OK, we need this real-time feature. We'll subscribe to a stream, and you can just say, I want to subscribe this little query on this stream, and then the server can send it to you, and you can load it from the side. And it just works because it was designed to work. So yeah, fix that problem. Update model doesn't change. So what's the state of the project? A design phase is done. It's actually been done for quite some time. A lot of it was just fixing all the bugs, and more bugs are happening, so we've got to fix more bugs. But there's not much more design work to do. We are rapidly approaching beta. It's great in that people are really using it, trying it out. The biggest problem is this lack of documentation. This is probably the first time that I've sort of enumerated the big picture and why OhmNext works the way that it works. And over time, we will actually probably do a lot of documentation, so it's clear how the various patterns, like things like, well, show me the optimistic update example. Show me how to defer a query, so on and so forth. And that's going to appear rapidly in the next few months. Conclusion. So my conclusion is that UI programming can be made radically simpler. I think Relay and Falcor just delivers a ton of inspiration on how you can simplify the thing. I think you can push it further, and that's what I've tried to do with OhmNext. Relay and Falcor are great. Now we can take it to the next step, and I believe that you could probably take it even further than that. But whatever we're doing now, I don't think it's great. So whether or not you use OhmNext, I think your UI system should have the properties discussed. And I think each one of these things they're not random features. Right? They're trying to solve a whole host of problems that I encountered over and over again when I was building UIs. Just a huge thanks to the ClojureScript community. I mean, it's one thing to have an idea, and it's one thing to have a community really validate the idea and really take it and basically make it real. I would not be up here with all this stuff if it wasn't for the amazing ClojureScript community really pushing these ideas and also sharing them. I think what's really interesting is when I started with ClojureScript, I was like, OK, ClojureScript's a little bit crazy, but it's kind of cool because I like Clojure. But it's really in the past year, it seems to me now, that actually ClojureScript and Clojure are sort of actually have this opportunity to sort of actually really push UI programming forward. It wasn't obvious that that would be the case, but I think collectively, I've seen so many amazing ideas happen. I think we're actually at the leading edge of UI programming, which is awesome. So thank you. Yeah.